All right, so yesterday, guys, did we finish with this one in this class?
Yeah.
Okay, we added them together. We found what f of b was and f of a, or g of a plus 1. We added them together. Yeah. Okay. That's going to be something we like to do eventually. If you've gotten through the first 2.1 assignment, towards the end, there's a handful that use like a plus h. We'll definitely do some examples of that. If we have time at the end of the period today, if not, we'll definitely do them tomorrow at the onset of the class. So you have some examples of that so you can work through those. It's the same concept, it's just that they're a little bit longer in regards to the algebra that's involved. But we have talked so far about kind of deciding whether a function, whether looking from a table we had functions, and then if it is a function, then we can gain what our output value is based off what input value we're using, right? Okay. Same idea here. What is our output value, for instance, in part A, if I use 4 as an input? Okay, or if I use -2 as an input, what are those outputs? And then can I add or subtract, multiply, divide those outputs? So that's fine. This is another way to look at a representation of a function and garner output values. Okay? Now when we look at this, what I want you guys to recognize is when we look at the definition of a function, when we start doing the notation, I don't know if I still have it up here. No, we'll leave it out. We said y equals f of x. Okay? Y equals f of x. So, when I see like something like f of 0, okay, f of 0, and it might even make more sense to write it initially. Let's see here. Tablet died. Oh, there we go. You know, if y equals f of x, then we also know f of x equals y, right? And maybe writing it that way might make you recognize that when I find f of 0, when x is 0, right? What are they asking me for? They're asking me for the y value on my graph that is associated with an x of 0. So let's go find x being 0. What's the y value on my graph? It's 1, isn't it? So this is a way of asking you essentially, what is the ordered pair? If you know x is 0, what's the other coordinate? What's the total ordered pair? So when I say f of 0 equals 1, I'm saying that 0, 1 is an ordered pair on my graph. Okay? Now a lot of times obviously you guys like to write ordered pairs as x, y, right? But when I write an ordered pair as x, y, or that's the notation I use, I am not dictating the type of relation that I'm using. Okay? But when I write x, f of x, do you now know, because of this rule here, this notation, that is essentially a y value, right? It's a range, it's an output. But do you know that it now came from a function? Yeah, we're using that notation, right? And that's going to be important. As we go through this course, guys, I had it drawn up, and I'll draw it up there again for you guys. As we go through this course, it's an investigation of functions. That's basically what all of pre-calculus is, with a couple additional things. Okay, we like to investigate and figure out what are functions, what relations are not functions, that kind of thing. So we've got this kind of all-encompassing grouping of objects called relations. Okay, and there are all types of equations and maybe even inequalities that you see. Let's just stick with equations, but there are all types of equations or graphs that you guys have seen throughout all of mathematics so far. Okay. Well, within relations, there is a subcategory. That subcategory is called functions. Okay? And then everything inside that subcategory is going to have the same characteristics that functions have, right? Does that kind of make sense? Okay? Inside this subcategory, we're going to have things like polynomial. I'll just write f of x for functions. We will have rational. We will have maybe logarithmic and exponential. We'll have trigonometric. We'll have root functions. Okay. And there's others. Okay. We'll talk about those other ones as we come across them. But everything in that group of functions, you know, there's something that makes polynomial functions different than rational, right? There's something that makes rational different than trig. Something different about trig than roots. Okay. But all 5 of these individual groups are going to have some aspects similar. Does that make sense? Because they're all kind of the children of functions, of that group of functions. Does that make sense, everyone? And that's what we're going to investigate. What makes them the same? What makes them different? Okay. And once it's not a function, and it's just in that overall purple box of relations, what can we do with that? Okay. And that's kind of what we investigate throughout the course. So these are what we're going through right now are just kind of generic functions. We don't really we're not classifying these. This one right here, this graph, is actually a polynomial function. But I'm not really worried about classifying them right now. I'm just worried about looking and saying, okay, how can I interpret information from that? Because the way I interpret information from that is going to be the same way I interpret information from any of these. Okay. So we've got the ordered pairs that we're going to write them x comma f of x. Now telling us that they are input and outputs, domains and ranges, but we know that they are coming from a function because of the notation that we're using there. Okay. So if I ask you what is f of -2, again I'm asking you what's the y value, what's the output value for the input of -2. So I go to -2, and what's the y value that's going to be on my graph? -3. So that generates the ordered pair, -2, -3. Okay. And if I try f of 3, f of 3 gives me my next value of 3. What's the output value? 2. If we zoomed in on there, it's not really hitting 2. It's going to be 3. If you got close enough, you can see it's not 2. But we get 3 comma 3. Okay? Is that all right with everybody? But, so that's asking you, with these x values, what y values are yielded or provided. Okay? We're going to reverse the order. We can say, okay, if f of x equals -3, okay, f of x equals -3, can you give me the x values? Look at this, what this is saying right here. We said f of x equals y, right? Well, look at how that compares down here. What is y now? -3, right? So the question is, if I have a y value of -3, what's the x value that's going to give me a point on my curve that has a y value of -3? What is that x value? 2 and -2, right? Okay. I get 2 answers there. And that's okay. That's okay because we don't violate. If I write these as 2 comma -3 and -2 comma -3, those 2 points, because some people say, well, you got -3 as a y value twice, and that's a problem. That's not a problem. The problem is when we have an x value having multiple y values, the same x value having multiple y values. That's what violates the definition of function. Okay? Function, remember, is a relation which every x value has one and only one y value. Is this one x value? Does it have only one y value? Yeah. Is this a different x value? Does it have only one y value? Yeah. And it's just by circumstance that these y values are the same, but that's okay because these are different x values. Okay. Is that something we can do? We can pluck those values off of our curves. Okay. You guys remember the vertical line test? Okay. Now it's down here in the next couple questions. Down here it says how to determine if a graph represents a function. We use the vertical line test. But I'm going to define that up here, talk about what a vertical line test does. Okay, so vertical line test says for any vertical line passing through the curve or our graph, it might not be curving, it can only intersect the graph one time for each x, else it fails. Okay, so if it intersects twice for a particular x value, it fails, right? Okay, and just like anything in mathematics, you could be passing this thing an infinite number of times and fail it once, and that's enough to say it fails overall. Okay. So passing the vertical line test then implies that you have a function. Failing the vertical line test just simply says you have a relation. It defaults it back to that larger overarching grouping of relations. Okay? So if we look at this polynomial curve up there, and there's going to be some features that we learn later on, but when I draw this vertical line in here, okay, will that ever intersect more than one time as I pass through there? Okay? Nope. Okay? Now what if I did this? What if for some reason there was a point right there as well? Do I pass all the way through up to here? Do I pass all the way over here? So I've passed an infinite number of times, right? Do I fail here at 1? Is that enough to say that's not a function then? Absolutely. Okay? So, when we're doing the vertical line test, that's kind of the idea, the concept that we're trying to target here. And if you're being asked, guys, to determine whether a relation is a function off of maybe different displays of information, like this is a display using tables, right? If you're asked to determine if it's a function and you struggle with it being in a table, or maybe I give you a list of ordered pairs, that's exactly what a table is, and you struggle to determine if it's a function or not, can you graph it and apply the vertical line test to that graph? Okay, so that's something we can always do. So if I look at this, what this is asking, is this a function? And what we have to do is apply our definition. Okay, because that's how we classify things, right? I'm gonna say it's a function, then this thing has to be meeting the requirement of what our definition says. So our definition of a function, if you remember, a function is a relation in which each x value has one and only one y value. Okay? I think yesterday we said input and output instead of x and y, but that's what we're looking for, okay? So does each x value, does an x value of 2 ever have a y value other than 1? No. Does 5 ever have a y value other than 3? No. Does 8 ever have a y value other than 6? No. So yes, this is a function. If you struggled with that, because eventually, I'm going to give you more than 3 points. Okay, you can plot these. I go 2, 1, we could go 5, 3. And 8, 6, right? So 4, 5, 6, 3, maybe something like that, correct? Okay. Now my graph does not have to be a curve. They don't even have to be connected. Does that make sense? It doesn't have to be what we call continuous. It's just the data points. And if I take my curve, I'm passing here because it doesn't exist over here, right? I'm only interested in where this thing exists. So at 1, do I exist? Is it a function? How many times will we intersect it? Just once, right? Just at that point right there. So I pass. Do I pass there? Yeah. Do I pass there? So did I pass everywhere? Yeah, so it's a function. Down here in example 2, example 2, do we satisfy the definition? No. At that 5, at that x value, we get an output of 2, and then here we get an output of 4. Graphically, what that's going to look like, we got 1, 0, point there, and then 5, 1, 2, 3, 4, 1, 2, 3, 4. So we have a point here at 5, 2, and one here at 5, 4. If I take my number or my vertical line again, now here's the thing: does it pass there? Absolutely. Okay, but does it pass there? No. And how many times do I need to fail to show that it fails overall? Just the one time. Okay, so that is not a function. Okay, you might be presenting now. They're showing you this in like a table here, but I could give you something, you know, like this. We're going 3, 2, 4, 5, 1, 0, and then 3, -3. And I ask you that, is that relation a function? So I go look and I say, okay, are there any x values that are duplicated, right? Okay, so I do have an x value that's duplicated, right? Do they have different y values? Yeah. Okay, so I got a y value 2, I got a y value -3 with that x value of 3. That violates the function. Okay? But that's just an alternative form of a table. Okay? All right. Is that thing a function based off the vertical line test? Absolutely. Okay. Is that thing? No. Does that ever pass the vertical line test? See some heads shaking? No. But there is one place that it passes the vertical line test. X equaling 0. We only intersect one time. But again, that's just one instance. We need to look at it at all possible values. So once I move to the right of 0, we start failing it everywhere else. Okay. Now that's a graph that we'll be interested in at some point. Okay. Circles pass the vertical line test twice. Everywhere else they fail. But circles are a relation that we're very interested in. Okay. So we will talk about relations that are not functions, and we'll talk about how they are different than functions and that kind of stuff. But right now, trying to decipher the difference between them. Identifying a function through the use of an equation. Okay. Kind of the default is to graph these things. Okay. Let's go to my calculator, whatever I use. I'm going to show you GeoGebra. And you can then apply the vertical line test, okay? Or you can actually solve for y. Solve for your variable, y, and see how many results you get. If I get double results or duplicate results for y, does that tell me I violate the idea of a function? Okay? So if that first one, is that a function? Do I have one option? When I choose an x value, do I get only one option for what y is? If I choose x to be 3, what's y going to be? 9. And that's my only option, right? If I try 3 1,000 times, I'm going to get 9 back 1,000 times. Okay? I only get one option there. So that thing is a function. But if I look at example 2, if I solve that thing for y, don't I get this? How many options then do you have for y when you plug in some x? you have 2, right? If I choose x of 4, you get the option that it's positive 2, or you get the option that it's negative 2. There's 2 results there, okay? Not a function. What about this one? Remember what the absolute value, remember we said like absolute value of x, when that is equal to c, we said x was equal to negative c, or x was equal to c, right? It's the same thing, it's just different variables. Now we're saying y is equal to x, y is equal to negative x, right? Okay? So I've got options, it's just like I had options up here. If I choose x to be 3, I could have y to be 3, or if x is 3, if x is 3 there, plug in 3, what do I get back? Negative 3. You see how that violates the definition? Okay. Down here, for example 4, do I ever violate that definition? No, there's only one option for y. Y is already solved for. All right, so if I get into GeoGebra, and the reason I like GeoGebra, if I look at some of these equations, okay, the ones that are solved for y, that is called an explicit equation, because you know exactly what y is. I'm telling you straightforward what y is. There's no doubt. There's no question. This is implicit, meaning that I'm implying or I'm kind of hiding what y is. You got to do a little bit of work to find out what y is, right? That's implicit. This is implicit. This is explicit. Telling you exactly what y is. Okay? Now, when we look at our calculator, TI-83 or 84, it is solved for y, right? So if I wanted to graph example 2, I actually have to do it with 2 different graphs to do it. Okay? Because example 2 is y squared equals x. Well, look at my calculator, it's solved for y, right? So I got to put in y1 radical x, and then y2 I got to put the opposite of x, okay? Or opposite of radical x. That's kind of a pain in the butt with that type of calculator, but that's what we call it. It's an explicit solver. Okay? It means your equation's already set up for you in regards to y. What is nice about GeoGebra and Desmos is that they are actually implicit graphers or implicit solvers. So I can type in y squared equals x in a graphic at one time. Okay? So you see then, does that violate the vertical line test? Yeah. And that's the idea that, bless you. If I go y equals square root of x, okay, and make that red. Okay, so that red part is the positive square root of x. This part down here, the black part, is negative square root of x. Is that okay with everybody? Do you see then when I choose x of 4, that's why I get a positive 2 or a negative 2, correct? Okay. Same idea happens with absolute value. If I go absolute value of y equals x, same concept, right? Okay, you're going to fail the vertical line test. So that thing's not a function. But we can do that. We can recognize it algebraically with autographs by solving for y and seeing if we get multiple options for what y is defined as. Okay? Obviously here we got y defined as root x and y defined as negative root x. And that's an issue for functions. Is that okay? Alright, so now this is kind of the information that I want to make sure that we are fully aware of, fully understand, grasp it real well. And this is kind of the reason why we've been spending so much time on interval notation and kind of nitpicking on that, because it becomes something we do all the time with these functions. We will, when we talk about polynomial functions, we'll do this for every polynomial function we come across. Okay? Then when we leave polynomial functions, talk about rational functions, we'll do this for every single rational function we come across. And we'll do that for every new function. We'll come back and we'll talk about what are the possible domains and ranges for these functions. Okay? When I talk about domains, those are your what? What values? What coordinates? Those are your x's. Okay? So what we're basically saying here, guys, is that we're trying to come up with a list of x values that our graph is defined for. Okay? Or that our graph is existing for. Another way of thinking about it is if there's an infinite number of points on all these graphs, right? It is impossible for us to go and list each one of those infinite number of points. But if we did, the domain value that we come up with, the domain interval that we come up with, would be representative of the only things that you put in the x position of all those infinite points. Okay? So when I look at this picture here, and I ask you what is the domain, we're looking now at a two-dimensional plane. We have now two number lines. We have a vertical number line and we have a horizontal number line, right? Okay? If I plug in this vertical line and I start moving it, I am moving it along the x-axis, right? So when I'm moving this vertical line, I'm actually asking what are the domain values. Okay? So my interest here, I'm going to put capital D, and I'm going to ask then what are the x values that my graph is defined for. The first place I come up to is 2, right? That would be the first x value. Now is it inclusive or exclusive? Exclusive, okay? Meaning that 2.00000, every time there's a 0, and then 1 is actually the first x coordinate that would be listed in all my ordered pairs, right? Now as I move this vertical line through, I just want to make sure that I list the x values that my graph is defined for. What is the last x value that on that interval that my x's are defined for? 8. Do I include 8?
Yes.
Yes. So my domain is 2 to 8. Okay. The next thing we're going to do then is deal with our range values. So it's a little bit different. This is the one that usually people struggle with. My range values, those are your y's, correct? Or your outputs. Okay. When we talked about this earlier, we haven't seen too many examples other than the one or two that I showed you in class. But when we talk about determining a interval on a vertical number line, okay? So as I move this green wall up, okay, I'm going from the bottom of the y-axis to the top of it, right? So you always read vertical number lines from the bottom up, okay? So as I move that, what is the first y value that my graph comes across? 6. Do I include 6?
Yes.
Yes. Okay. So 6 is included. Now what would be the last y value that comes across? 8. Do I include 8? No. Okay. So there are my domains and ranges. And what that means, guys, is if I were to list the infinite number of points that exist on that little segment, there would never be an x value of like 9 or 17 or 30 or something like that. These are the only x values that are going to be identified if I were to write the infinite number of ordered pairs here. These are the only y values that would be identified if I listed the infinite number of ordered pairs. Is that all right? Okay. You always got to go bottom up because remember, this number here always needs to be smaller, right? Okay? Or further to the left on a number line. Yes?
Why do we usually struggle with range?
Because they want to go top to bottom. They want to rewrite it as 8, 6. Okay? Because that's how we read, right? We go left to right, and then top of the page, bottom of the page. But when we do a graph, we go left to right, bottom page to top of the page. The way we should kind of interpret it. All right, so now, let's do this one over here on the right. There's a little bit of an intricacy here with, I think, our range. So if I go domain, take my wall here and start passing through. What's the first x value that that wall passes through? -5. Do I include -5? Yep. Okay. I keep going, so none of these values are being removed. And then I get to 3, right? Do I keep 3 or do I exclude it? Exclude it. Is that okay? All right. So then we do the range. Bottom up. So I go go bottom up. What's the first y value that this green line is going to? Yeah, first y value is going to be 0. Do I include it? Yeah. Okay. So all of these points here, guys, are viewed as being solid dots, right? Okay. So here I am. That is a solid dot. That ordered pair has a y value of 0. Keep moving that thing up, and we get to where the kind of the intricacy of this problem occurs. And the question is, do I include 3 or do I not include 3, right? Or sorry, 2. 2 is the y value, right? Do I include it or do I exclude it? You include it, because remember what that means is that that is listing options for y values out of this graph. And if I graph or I list all these ordered pairs, isn't -5, 2 going to be an ordered pair? So if that's going to be an ordered pair, then it has to show up in my range down here as a potential for that y coordinate. Okay? I want to do 2 minutes here. We can do this next one. Okay? What's my domain going to be? What is my first x value that I come across on this curve? -4. Do I include it or exclude it? Include it. Now as I move my vertical wall through there, what would be the last y or x value you come across? Infinity. You got to pay attention to those arrows. Okay. They're gonna provide us a lot of information. My range then, -2 to infinity again. Okay. When we see this, we're gonna interpret it as, it's kind of at an angle here, right? So it's continually rising. It might be real slow as it rises, but we're saying it's going to rise forever. So we get to a y value of infinity. We'll do that next one on that fourth one tomorrow. And we'll also go through and see a couple more of these tomorrow that we kind of maybe remove some points and see how that changes our domain and our range and that kind of stuff. Okay? Please make sure you start looking at those assignments and come with maybe some questions we talked about.